Hello, everyone. Welcome back. Today, we are going to be solving problems with exponential and logarithmic functions with a focus on word problems this time. Because I know last time we talked about how to solve logarithmic functions. Today, we're going to talk about specifically with word problems what we mean by that. So let's start with example one. It says, three earthquakes occurred in locations A, B, and C with magnitudes 4, 6, and 7, respectively, on the Richter scale. How many times stronger was earthquake B than earthquake A? And how many times stronger was the earthquake at C than the earthquake at A? Okay, so when it comes to the Richter scale, we know that this scale going up by 1 is actually multiplying by 10, right? A multitude of 10, okay? And so if we're going from A to B, which is the first one, from A to B, well, A's power is 4, and then B's power is 6. So we have to go up 2, right, to get there, right? So we have 5, and then we have B, which is at 6. And we're going to go up 1, which is really times 10, right? Because anything on the Richard scale going up by 1 is really times 10. And then times 10 again, which is 10 squared or 100. So therefore, B is 100 times stronger than A. And we can do the same thing with C, right? Here we have A, which is 4. And then we have B is 6. And then C is 7, right? So to get from 4 to 5, it's 10 times. To get from 5 to 6, it's 10 times. To get from 6 to 7, it's 10 times. And so therefore, we have 1,000, right? 10 times 10 times 10 is 1,000. So therefore, C is 1,000 times stronger. Oh, stronger than A. Awesome. Okay, so let's move on to example 2. Example 2 says if one earthquake has a magnitude of 3.5 on the Richter scale and a second earthquake has a magnitude of 6.2, compare the intensities of the two earthquakes. Right? So they want to know basically how many times stronger is the 6.2 as compared to the 3.5. So to compare, we're going to say, well, the one has the magnitude of 10 to the power of 6.2, and the other one has the magnitude of 10 to the power of 3.5. So that means we have 10 to the power of 6.2 minus 3.5, which is 10 to the power of 2.7, which is 501.19 approximately. So therefore, the second earthquake is 501.19 times stronger than the first. So I think we're getting the hang of this now, right? That the Richter scale, it's a scale of powers of 10, right? Every time we go up 1 on the Richter scale, we're really multiplying by 10 times the intensity, right? Every single time we go up 1, right? And so it's different. It's different than what we're used to because this has to do with like our logarithms, our exponents. Okay. So what about example 3? It says according to the table given out in class, amplified rock music has a loudness of 120 decibels, an ordinary conversation has a loudness of 50 decibels, and a whispering has a conversation of 20 decibels. How many times louder is an ordinary conversation than whispering? Okay. Well, when it comes to the loudness scale, going up 10 on the loudness scale is multiplying by 10 in terms of intensity, right? So if we have a loudness of whispering, so whispering is 20, right, is 20 decibels. Then we have 30, 40, and then 50 is the ordinary conversation. Each time we're going to go up by 10. So let's write that in. So here, from here to here, it's times 10. From here to here, it's times 10. And from here to here, it's times 10. So that's 1,000, right? 10 times 10 times 10 is 1,000. So therefore, ordinary conversation is 1,000 times louder than a whisper. Okay. Well, I mean, at least according to this, I don't know how accurate these are. I'm not a science person, but assuming that's accurate, that's kind of crazy. 1,000 times more than a whisper. Okay. Let's do B, which says how many times louder is a rock concert than an ordinary conversation? So an ordinary conversation is 50. Then we have 60, 70, 80, 90, 100, 110, and then finally 120 for the rock concert. So each of these are times 10. So we have times 10, times 10, times 10, times 10, times 10, times 10, and times 10. So 1, 2, 3, 4, 5, 6, 7. So 7. So 10 to the power of 7 times louder. So ordinary conversation, or I guess I should say rock concert, is 10 to the power of 7 times louder than the ordinary conversation. Good. All right. Example 4 says the sound of a person screaming is 104 decibels. The noise level of the same person shouting is 87 decibels. How many times louder is the scream over the shouting of this person? Sounds like they can scream louder than they can shout, which is interesting. Okay. So to compare, in this case, we're going to do 10 to the power of 104 over 10, right? Because in this case, to go up 10, we multiply by 10, as opposed to going up 1, we multiply by 10. So that's why we have to divide by 10 here, right? As opposed to Richter's scale, where we didn't do this, because going up by 1 on the Richard scale is like multiplying by 10. And that's going to be over the screaming, which is 887 over 10. So that is 10 to the power of 10.4 over 10 to the power of 8.7, which is 10 to the power of 1.7, which is 50.12. So therefore, the shouting, or I should say screaming, because screaming's the louder one, screaming, for this person at least, is 50.12 times louder than shouting, which that's interesting. I would have thought it wouldn't have been that much, but that's a lot. Good. Okay, very good. Okay, let's move on to this chemistry example. In chemistry, the pH, the measure of the acidity or alkalinity of a substance, is based on the logarithmic scale using the formula pH equals negative log H plus, where H plus is the concentration of hydrogen ions in moles per liter. A says find the pH level of a substance if the hydrogen concentration is 0.000001 moles per liter. Okay, so in this case, we know we just have to plug this back in. We know that pH is going to be equal to negative 0.000, there's 1, 2, 3, 4, 5 zeros, 1 moles per liter. Oh, sorry, I forgot to put log. It should be negative log and then H plus 0.000001 moles per liter. And then what would that be? Well, 10 to the power of what is going to give us 0.000001, Well, we'd have to move this decimal point over 1, 2, 3, 4, 5, 6, 7 places, right? In order to get back to 10, right? So that's a lot of places, 10 places. 1, 2, 3, or sorry, 7. I think, why did I say 10? I meant 7, I think. Yeah, because we'd have to go 1, 2, 3, 4, 5, 6, 7 to get it back to just regular 10. So 10 to the power of negative 7, therefore, would be 0.00001. So therefore, the answer is negative 7. And therefore, the pH would be 7, because minus negative 7 is just going to give us regular 7. Then it asks, find the hydrogen concentrate level of a substance that has pH of 9.3. Okay, so in that case, what we'll do is we'll put 9.3 for pH, and we'll put over here negative log of H plus, and that's what we're trying to figure out. Okay, so first things first, let's put the negative on the other side. So negative 9.3 equals log H plus. And now let's change this into exponential form. 10 to the power of negative 9.3 is going to equal to the hydrogen plus. And well, that's it. That's the answer, right? We could do that out and say that H plus is equal to 0.00000000005 if we wanted, right? Because 1, 2, 3, 4, 5, 6, 7, 8, 9. We could do that if we really wanted to do so, but this answer is perfectly valid too. So I'm just going to leave it like that. I think it's much nicer to write it that way. Very good. All right, and then example 6 says the amount of water vapor in the air is a function of temperature given by the equation S equals 5.06 times 1.07 to the power of 0.95 T, where S is the saturation of the air in milliliters per meters cubed, and T is the temperature in degrees Celsius. Find the temperature of the air if the saturation is 50 milliliters per meter cubed. Okay, so to find the temperature, we want to find T if S is 50. Okay, so let's plug that in. That 50 equals 5.06, 1.07, 0.95 T. Like that. Okay, and then let's divide by 5.06. 9.88 is equal to 1.07 to the power of 0.95 T. All right, and then we're going to log both sides. So we're going to say log 9.88 is equal to log 1.07, 0.95t. Because now what we can do is we can put the 0.95t at the front, right, as the coefficient, because that's one of our logarithm laws we talked about a couple days ago. So this is the same as 0.95t times log 1.07, and that's equal to log 9.88. So therefore, 0.95t is equal to log 9.88 over log 1.07. Good. All right, and what does that mean for us? Let's see. So that means T would be what? T would be about 35.5 degrees Celsius. And there we have it. Awesome. Okay. Next one is find the temperature of the air if the saturation, so if S is 5 milliliters per meter cubed. So instead of 50 this time, we're just going to do 5. Okay? All right, so let's do that. So that means 5 is equal to 5.06 times 1.07 to the power of 0.95t. So if we divide both sides by 5.06, we're going to get 0.99 equals 1.07 to the power of 0.95t. Okay, then we're going to log both sides. So we're going to get log 0.99 equals log 1.07 to the power of 0.95t. And then we'll put that 0.95t out front. So 0.95t log 1.07 is equal to log 0.99. And then so therefore 0.95t is equal to log 0.99 over log 1.07. Okay, so therefore t would be around 0. I guess negative 0.16 degrees Celsius is a bit more accurate though, so we'll go with that. All right, well, there we go. Congratulations on completing this unit. Oh, and I should mention here's actually a copy of the decibel scale and just some things we can kind of compare it to. And then also the Richard scale. Here's a copy of the Richard scale as well. But yeah, that is it for today. Good work today, everyone, and I will see everybody in the next unit. Bye, everyone.